The electron is detected at a distance of 0.8 meters from the emitting nucleus as measured in the laboratory. For the reference frame of the electron, calculate the distance traveled by the detector. Okay, so in the reference frame of the electron, the start and end points are going to be in motion, so the length is going to be contracted. And so we have L is equal to L naught over gamma. And for the electron, we're going to get 0.8 divided by, and then we need gamma, and gamma was 0.9, sorry, V was 0.975. So we get let's just work out gamma over here. So gamma is equal to 1 over the square root of 1 minus V squared over C squared, which is equal to 4.5. And so this is going to be 0.8 divided by 4.5, which is equal to 0.178. By the way, if you used 0.98 C for V here, you got a slightly different answer, and that would have still been marked correct. This is in meters. For the reference frame of the laboratory, calculate the time taken for the electron to reach the detector after its emission from the nucleus. Well, we use the equation V equals D over T. For the laboratory reference frame, D is 0.8, and T is what we're actually trying to work out. In fact, let's just rearrange this first. So T is equal to D over V, which is equal to, well, we know that D is 0.8, and we know that V is 0.975 C, and that comes out at 2.74 times 10 to the negative 9 seconds. Okay, again, if you'd used the rounded value of 0.98, you would have still been marked correct. For the reference frame of the electron, calculate the time between its emission at the nucleus and its detection. Okay, so for the reference frame of the electron, there are two ways to go about this. One is that we can use the fact that T naught is equal to T over gamma, and because the electron measures the proper time, the electron's going to measure T naught. So, and then we can use the time that we calculated in the previous question. So, looking back at the previous question, we had a time of 2.74 times 10 to the negative 9. So we can go equals 2.74 times 10 to the negative 9 divided by 4.5, which turns out to be 6.08 times 10 to the negative 9. Okay, alternatively, what we could do is use the fact that we know how far the electron has traveled because its length is contracted. So we know that D is going to be 0. What did we work it out to be? Let's go back and have a quick look. 0.178. D is equal to 0.178 meters. And we know that V is equal to 0.975 C. And so T is equal to V over D. Oh, sorry, other way around. D over V, which is 0.178 over 0.975 C which is 6.08 times 10 to the negative 10 seconds. This is negative 10, not negative 9. Seconds. Okay, outline why the answers to B3 represents a proper time interval. Okay, because, well, we can say for the electron, the two events, emission and detection, occur at the same point in space. And that's how we define the proper time interval. The proper time interval is the interval between the events as observed by a person in a reference frame in which the two events appear to happen in the same point in space. Not appear to, they do happen in the same point in space.